All right, so today we're talking about gravity. Now, we have talked about gravity before, and when we did so, we talked about how the gravitational force was calculated near the surface of Earth. So let's just review that quickly. So to calculate the gravitational force near Earth's surface, we simply use the equation: the gravitational force is equal to the mass of the object times the gravitational field strength on Earth, which we say is approximately 9.8 newtons per kilogram. Now, there's a story about Isaac Newton, and it goes that he was sitting under an apple tree and an apple fell and hit him on the head, and voila, he thought about gravity. And he didn't think about gravity, but a lot of people think, oh, well, he was the first one to discover gravity. But lots of people knew things fell at this point, okay? Newton was not the first. However, he was the first person to look at, wait a second, the apple just fell on my head. I can see the moon up there. Why is the moon not falling on my head? Okay. So while Newton did not discover gravity, he did discover that gravity extends throughout the universe. So let's go ahead and take a look at Newton's law of universal gravitation, which says if the force, which again he was thinking, if the force of gravity is being exerted on objects on Earth, what is the origin of that force? Where does it come from? And his realization was that the force must be coming from the Earth. And then he further realized that the force must be what keeps the moon in orbit. So the moon is falling, is what he figured out. It's just not falling straight down. And the reason it's not falling straight down is because of its tangential velocity that it starts with. So if we're looking at this picture right here, this is supposed to be Earth. And then on top of this is a cannon. And this is Newton's thought experiment, okay? So he was thinking, okay, we have a giant cannon and we fire it. Well, it's going to follow that parabolic path that we talked about earlier this year. If I fire it a little bit faster, it's still going to follow that parabolic path, but it's going to go a little bit further before it hits. And what he theorized is if it has just a specific tangential velocity to start, it is going to come back and end up exactly where it started. So gravity is pulling it the whole time, but it just keeps going around in orbit. Okay, if it was going too fast, it would kind of go around and then fly off to the side. Okay, so this gravity is what's keeping it in orbit. So this is where Newton is famous for gravity. He didn't discover gravity on Earth. What he did was take it and apply it throughout the universe. The gravitational force that is being exerted on me right now and you right now is only 1/2 of a third law pair. Remember Newton's third law: for every action, there is an equal and opposite reaction. So the Earth is pulling downward on me, but I'm also pulling upward on Earth. However, because there is such a disparity in masses, I am so significantly much smaller than Earth is, okay? The reaction force is undetectable. The acceleration is just too small. However, for bodies of more equal mass, it can be more significant. So again, we've got the moon here, and the moon is pulling on Earth, and Earth is also pulling on the moon. So what he determined was that the gravitational force must be proportional to both masses. So our equation that we had before isn't as precise as it could be, okay? We need to include both masses in this equation. And that he observed that the gravitational force must decrease as the inverse of the square of the distance between the masses. So again, the further away an object is from Earth, we call that the radius, okay? The smaller the force is going to be. So we're going to divide by that. But even more so, we actually square that, okay? So we divide by the square of that distance between the center of masses of the two objects. So the further the objects get away, the smaller and smaller the force between them gets. So in its final form, the universal law of gravitational looks like this. The gravitational force is equal to the universal gravitational field constant, which is the number 6.67 times 10 to the negative 11th. And then these are the units. Newtons times meters squared divided by kilograms squared. So that's the constant. Then you have the first mass, then you have the second mass, and then you have the distance between them squared. So the reason we could use our simplified equation before is because one of these masses was just Earth, and then the distance between the center of masses is roughly Earth's radius, okay? Yes, it would be, you could actually go ahead and calculate and figure out if you're in Death Valley, you're gonna have a greater gravitational force than if you're on Mount Everest, but they are very, very close together. So if we take the mass of Earth times the universal gravitational field constant and divide by the radius of Earth squared, we're gonna get roughly 9.8. So that's where we got our F times the mass of the object times that 9.8. All right, so we're gonna go ahead and try a problem together, but that's gonna be another video because I don't want this one to go too terribly long.